Thanks for coming again. This is the last lecture that I'm going to give on the subject of Higgs bundles and integrable systems. And what I want to do today is continue the theme of real slices of the Hitchin vibration and tell you certain slices that will appear in the Hitchin vibration which are related to the theory of three manifolds and their representation. And I want to also tell you about Langland's duality and how these slices may go through Langland's duality or mirror symmetry. And finally, I want to tell you some other correspondences which are not Langland's duality, but which appear between vibrations. So in our setup, let's go back to just writing the things that we're going to use. Sigma is our compact Riemann surface of genus at least 2. K is our canonical bundle. K is the cotangent bundle of the Riemann surface. What we had said yesterday is that we were going to take a complex group, GC, complexly group. So here we're taking either the general linear group or groups of type A, B, C, D. And G was a real, so all this information allows us to define GC Higgs bundles. If we make a choice of a real structure on the group, we can define real Higgs bundles. So let's put here G, real form of GC. And the real form is fixed by an anti-holomorphic involution, so fixed by anti-holomorphic involution sigma. And this allows us to define the real Higgs bundles, so G Higgs bundles. In the moduli space so we can construct the moduli spaces of complex Higgs bundles and of real Higgs bundles. And one thing that was given for us is the maximal compact subgroup. So we're going to call here ρ the anti-holomorphic involution fixing maximal compact. Of the complex group of GC. So all this information, what we've done is we've chosen a complex group and we've chosen a real form of the complex group, and we have our Riemann surface here. So we're going to take the moduli space again. We're going to put the setup that we saw a little bit yesterday and then carry on in more depth into those slices. So we have the Hitchin vibration. Vibration here into what I call A, that in Motohiko's talk was the B, the Hitchin base. H, this is our integrable system, so this is the Hitchin map. And what we want to do is look inside at real slices, so slices which are mid-dimensional submanifolds of our moduli space. And the way that we saw that we could do it is by looking at involutions. So the first involution that we saw yesterday, we said that GC Higgs bundles, G Higgs bundles appear as fixed point set as fixed by an involution that sends E phi, an isomorphism class, an involution acting on this moduli space, sending an isomorphism class to sigma rho E minus sigma rho phi. And we mentioned this was the way in which Hitchin constructed the Hitchin component back in '92. So this is following the idea of Hitchin in '92 in his Teichmuller paper. So let's call these I1. And when we look at these fixed point set, so G Higgs bundles appear as fixed point sets of this involution, and this gives a BAA brane. So let's put it with some color and let's just remind ourselves what these branes were. BAA A brane. So in our setup, we forgot about what was supported on this brane, and we said a holomorphic submanifold is a B brane, and a Lagrangian submanifold is an A brane. And we fix the three, in order to put the trio of letters, we fix in our family of complex structures and symplectic forms that we have from the hyper-Kaehler structure of the moduli space, we fix three complex structures, I, J, and K. And for your reference, in case you're wondering which one is which, and you can remember, this is the one coming from the Riemann surface, this is the one coming from the flat connection or complex group. So with respect to each of these three complex structures, we say that a brane or a subspace is a complex submanifold, a Lagrangian submanifold, and a Lagrangian submanifold. And we were interested in constructing the other types of branes that are available to us and to study the moduli space of Higgs bundles, the Hitchin vibration, and what are these slices with respect to the integrable system? What are they telling us? We studied a lot the spectral data for these fixed points. So lecture 3, yesterday we studied the spectral data for those fixed points. Now, we mentioned that if we have a real structure on the group, we can also take a real structure on the Riemann surface. So we're going to make another choice. So fix also. The next thing that we're going to fix here is going to be a real structure on the complex surface. So a real structure. And we saw yesterday that we could define the third involution here, let's call it, well, a second and a third involution. I2 send E phi to F star rho E and minus F star rho phi. And now I want to tell you more about these fixed point sets. So these fixes an A, B, A brane. So what are these fixed points? We saw that these ones could lie inside the moduli space, intersecting the smooth fibers in finite points, or in positive dimensional spaces, or in no points at all of the smooth fiber. And from those cases, we analyzed the one with positive dimensional intersection. I'll tell you more about the other cases in a second. The case of I2, this is the setup that we have with David Baraglia, and when we studied these ABA branes, we could see the following. So one of the reasons why we're interested in these spaces is because the representations here into, so the representations of the fundamental group into the complex group appear related to this brane in the following way. So we want to define, I mentioned that it was related to three manifolds, but now I need to tell you which three manifolds and how is the relation. So let's take a look at these branes and study some properties of these branes. So properties of these A branes. The first thing that you can do is you can try to understand how does it intersect the Hitchin vibration. So we need to understand what are the fixed points of the involution, this involution on each of the fibers and on each of the points in the base. And what we're having here, our starting point is an involution on the Riemann surface. So we have our Riemann surface, we have an involution acting here, F, which has fixed points. Fixed points of real structures on Riemann surface are circles, and as a real structure, it has two invariants that are going to label each of these real structures. So the invariants are, and the two invariants are usually called N and A, where N is the number of circles, so fixed circles, and A is, sorry, it's either 0 or 1. It's 0 if, I think it's usually if, when you take the Riemann surface minus the set of fixed circles. If this is gamma I, each of these circles are gamma I. When you take them out, it is connected. And one if this thing here has two connected components. So when you take your circles, you already know these, when you take your circles from your Riemann surface, you'll have either a connected space or have two connected components. The next thing that you can ask is, we have an involution on the Riemann surface, which implies we have an involution on differentials on the Riemann surface. So there's an induced involution here, an induced involution from F. It also implies that there's an induced involution on your spectral curve, which is a cover. So over here, we're going to have a cover. So the spectral curve, S, spectral curve, given by points in the base, will have an induced involution because there was an induced involution on the differentials. So there's an induced involution here. Let me just call it F again, because it's the lift of the involution on this one. So you may ask, what's the relation between the fixed points, what's the relation between the fixed points of the involution F and the ramification points of your Riemann surface? So you have your ramification points here, and you will have to check whether they lie inside or outside your fixed point set. So let me call the following. If we have this one, let's put it here, we'll have some which are fixed points and some which are not. So let's call in our setup, let me call U the number of ramifications fixed by F. And let's call N0 of all the circles. Of all the circles that we have, let's take the ones that don't have any ramification point. So number of circles without ramification points. Why are we doing this? Because we're constructing these branes starting from an involution on the Riemann surface. So we need to, yes? Z-wise fixed. Z-wise, I think, yes. Yes, yes. So indeed, so let me just put, that's a great question. Thank you, Motohiko, because there are equations that these two numbers satisfy. So in particular, let's put them here. The number of circles is between 0 and g plus 1. And you can have, you have two other equations that they'll have to satisfy. If there is no fixed circle, so if n is equal to 0, then when you take it out, it is connected. So A has to be 1. A has to be 1. And if G is if n is the maximum number of circles, is G plus 1, then it has to be connected, 0. And if it's the maximum, it has to be disconnected. A is equal to 1. And the other case that is disconnected is any time that you're congruent to G plus 1 mod 2. So any time that n is congruent to G plus 1 mod 2, you know that it is disconnected. Now, Gross and Harris studied these real structures on Riemann surfaces, and they showed that given a pair NA, which satisfies these conditions, there is a real structure on the underlying manifold that there is an involution on the underlying manifold, which is a real structure from some Riemann surface. So these pairs is up to some equivalence. These pairs classify our involutions, and hence, if they classify our involutions, they will have to classify, to some extent, the structure of our brane. And that's what we're trying to do here. We're trying to look at all the invariants involved and figure out what's going on. So the next thing that we need to see is what is the Higgs bundle on this manifold. So we have the Higgs bundle on the Riemann surface here. We'll have our E phi. Our E phi will be a fixed point of the induced involution, which means over each point, over each fixed circle, the vector bundle E, or equivalently, we have our spectral line bundle. So this is spectral line bundle. over each of the fixed points or fixed circles, there will be an action, induced action of the involution. So these objects, let's here note, over each fixed circle, gamma I, the vector bundle acquires a plus minus 1 action by F, or from F. So what's going on here is very similar to what we were talking yesterday, where we had a plus minus action of an involution on the spectral curve. Here we have a vector bundle. The vector bundle is preserved, and over each of these circles, it's sending the vector bundle to itself. So we have a vector bundle of certain rank, so in each dimension, it's acting as plus or minus 1. So this action of plus or minus 1, it's giving us a class of the vector bundle, so it's giving a class of the vector bundle E in the reduced equivariant K-theory of the Riemann surface. So there will be a class, and we'll not go further into what it is, but you should think about it in the same way that you were thinking about invariance for real Higgs bundles coming from actions of involutions on your spectral curve. On the fixed points, you will have some action, and the action of this involution on these circles and the number of circles will all be interrelated. So now you can ask, okay, what is this brane, and what is it giving us? So let's put just here a theorem that we did with David, Laura Schaposnik. So what we showed is that this brane actually lines as a possibly singular Lagrangian vibration. So the ABA brane is a possibly singular Lagrangian vibration. So it's giving a real integrable system, and when you look at the smooth fibers of this brane, so the smooth fibers, the intersection of the brane with the smooth fibers, you have a collection of tori. And when you want to understand how many tori they are, you go back to the invariance and you figure out from there. So the intersection with the smooth fibers is a collection of tori, is a collection of tori. And you may ask, okay, what's the collection of tori? Let's just try to see what it is. In the case of the Jacobian variety, so let's look at examples of what can we try to understand from here. In the case of the general linear group, let GC be GL and C. So in the case of the general linear group, we have the classical Hitchin vibration. Our fibers are Jacobian varieties, and we're looking at real points in Jacobian varieties. This is what Gross and Harris were doing in their real algebraic geometry paper. They were looking at real points, and that's where you can show, in this case, how many tori they are based on real points on Jacobians. So here, the next thing to do is look at real points in Jacobian varieties. You can ask also what happens in the other cases. When you start putting subgroups of GL and C, so you're going to more complicated Higgs bundles or Higgs bundles with further constraints, it becomes more and more difficult to understand how many tori and how they lie. Now, in the case of SL and C, let's come here, for GC equal to SL and C, your spectral data and the fixed spectral data that you're trying to understand depends on the fixed points of the involution and the ramification points that you're fixing. So the number of tori that you actually get, so the intersection with the smooth fibers the intersection. And remember that for SL and C, our smooth fibers are prime varieties, so the intersection with the prime variety of the curve and the Riemann surface, what does it tell us? It's a collection of tori, but how many is a collection? And what we have to use now is this invariance that we define here, the number of circles without points and the number of ramification points fixed by the involution. So what you get here is a collection of 2 to the n0 plus u over 2 minus 1 tori. And you can carry on and try to, we stopped in SL and C, but you can carry on and try to understand how many tori are in this fibration. So in the intersection of the smooth fibers with this brain. One thing that we haven't understood yet is you do get a real integrable system, but what is it governing this system, or why is it interesting beyond what I'm going to tell you about three manifolds is still an open question. So let me tell you why also it's important, the fact that we have this action and the fact that we constructed a class for this vector bundle. So we have the representations of our Riemann surface related to complex Higgs bundles. If we look at representations into real groups, we'll look at real Higgs bundles. What can we say about representations for these branes? So I'm going to just look here at what's the relation with representation theory of these things. Because then you'll understand why we're looking at the different circles and the different properties of this map. What I want to do now is I want to look at three manifolds. I want to construct from our Riemann surface a three manifold whose boundary is our Riemann surface. So I want to construct, and let me just draw it like this, very badly, as a manifold M, a three manifold M, whose boundary is sigma. So let M, and it's going to be a very particular one, but it's going to include handle bodies and it's going to include a lot of things that are interesting. Let M be the product of, so it's called the I bundle, I think. The manifold, the Riemann surface, tensor with the interval, and now we're going to quotient by an involution that sends a point in the Riemann surface and a point in the interval to the involution on the Riemann surface and minus the point in the interval. This is a three manifold, so this is a definition, is a three manifold. And if you look at the boundary of your three manifold, this is your Riemann surface. So you can ask, and the question that you can ask it for any three manifold, but we can answer just for this one at the moment. So the question here is which Higgs bundles extend from the Riemann surface to a three manifold, or as flat connections, which flat connections extend from the boundary of your three manifold to your three manifold itself. So which connections extend, or which representations, if you want in that setup, extend from representations of the fundamental group of your Riemann surface to representations of the fundamental group of your manifold. You really will have to have orbifold here, orbifold fundamental group. And the answer comes from the structure of your Higgs bundles, and you knew that your ABA brane was a collection of tori, but these tori are labeled by our invariants, and so they will have different properties. And the theorem here is that only the ones that have a trivial class will be the ones that extend. So the theorem with David Baraglia is that the representations that extend are or correspond to Higgs bundles E phi, for which or such that the class of E is trivial. So it's a direct way of choosing or selecting the Higgs bundles that correspond to representations that extend. So let me tell you just in 1 second why this is also would also be interesting to do it in another setup that is not being done. So one thing that I put here is that we were working with genus at least 2. If you could do this analysis and construct the 3 manifold through the involution for genus 1, what you are going to be understanding is representations that extend from the complement of a torus. So you take a knot inside a sphere, and you look at the representations that extend from the complement, from the boundary of the complement of the knot to the 3 manifold itself. Those objects are selected in the theory of knots by the A polynomial, but here they would be selected by the ABA brane. So you would have, if this was done for genus 1, you would have a way of relating your A polynomial to these invariants appearing from real structures on your Riemann surface. So that's something that is yet to be done. Yes? Mm-hmm. What, sorry? It sounds like what? So I don't know their papers. So what do they look at? Okay, so it's no Higgs field. So, but it's a question that's, I'll take a look. So it's a question that knot theorists are looking at it a lot from knot theory perspective, so with the A polynomial. And we haven't looked at it yet from this perspective of branes. We know so anytime that you have a 3 manifold with boundary and you ask the question what representations extend, you know that it's going to be an ABA brane inside the moduli space of representations or Higgs bundles. So you know that it's going to have this structure. That's the first thing. But you don't know how to construct it. This is one way to construct it for this one particular case of 3 manifolds. Now there's another thing. So we're trying to match up with knot theory. One way is by saying, let's put genus 1 here. Another way is by saying, let's not match up with knot theory, but with links or graphs. And the theory of complements of graphs and representations that extend has also been studied. And that's through the generalized A polynomial. So that's another thing that could be matched, and now with this thing here. No, I haven't done it, but it would be natural. So if you take a 3 manifold without boundary and looking at a Hegel decomposition, indeed the Caston invariants should be related to this invariant here in a natural way. You would probably get this. Yeah. Yes, it would be I think it would be very interesting to do it. It would require some computations of Caston invariants and these ones, but it would be very interesting to have the relation of these 2 objects. No, I don't think so. Oh. The Caston invariants, yes, they have been defined, but not in terms of branes, right? No. It was with Lagrangian, yeah. Yeah. So those are properties of, I can't see the time, 30. Those are properties of this ABA brane, and these are some open questions that if you are interested, I'll be really happy to talk about, or you should work on them. So another question that you may ask, and now we're going to go into some bits that I wanted to tell you about this other brane we saw yesterday. Another question that you can ask is, which other mid-dimensional branes can you get, and how can you get them? What's our natural ways of getting them? We mentioned that there would be some natural but too simple ways, so taking subgroups could be possibly too simple, but we could try to do something else related to involutions. And let me just leave here these, and I'm just going to make one comment in case anyone can think of more questions related to these. So one other question that you can say is, we've used a real structure F. What happens if we use actions of finite groups? So what happens if I put here the action of gamma, finite group? The first question you can ask is, how can I get a mid-dimensional brane? So all these branes that we talked about, the ABAs, the BAAs, they're all mid-dimensional Lagrangians. So how can we get mid-dimensional Lagrangians? So the thing that one can prove, so let me just put it here. I'll put it smaller here. So gamma finite group. And one thing that you can show, and you can start working from there, so you can see which kind of groups will give you mid-dimensional submanifolds, actually. So the theorem with Sebastian Heller and I were, in a paper we're finishing, is trying to describe all the types of groups that can act on your Riemann surface and can produce for you mid-dimensional, in this case, BBB branes. So finite groups, so only finite groups with order or of order multiple of 2 produce mid-dimensional B branes. So these are holomorphic branes with respect to each of the complex structures. Now I'm just being very rough here. I can tell you more. You can only have these type of branes appearing on Riemann surfaces of genus 2 or 3, and the groups are actually just 2 cases in each. So you have the action of Z times Z in one case, and you have the action of Z times Z for something else in another one. But there's not many cases, and you can't do it for higher genus, actually. Anytime you have these finite group actions, you won't be able to get these branes. Now, why do I care that much about these BBB branes? We will see in a second what Langland's duality does and why BBB branes are also important. But you can also ask, what happens now if I have this finite group action and my F acting at the same time? What am I going to get? The way that we construct these branes has to do with the way that you construct constant mean curvature surfaces, so CMC surfaces. And if there's the two, you get what we want to call CMC branes, which is a mixture of an ABA brane, so a Lagrangian subspace, with something coming from constant mean curvature surfaces. So if you're interested, I'll tell you more about this in a second. But let me tell you about this other brane, and actually, let me also tell you what happens with Langland's duality. Because here we had the moduli space of Higgs bundles, GC, for the Langland's dual group. And we said here, I erased it, but I really want to put it again so that you can try the guessing game and tell me what the duality should be once I tell you the structure. So here we had this involution acting on Higgs bundles, and we looked at fixed points, and we said this gives us A, B, A branes. Now Langland's duality tells us not what the dual brane is, but it tells us what the structure of the dual brane should be. So talking about the basis only. And it tells us if you have a BAA brane on the dual side, so here is mirror symmetry, and it tells us in the dual side you should have a B, B, B brane. And in the dual side here, this is self-dual type, you should have an A, B, A brane here. Now, when you think about how these branes were constructed, let's look at the I2 brane. The I2 brane was constructed through an involution on the Riemann surface and a compact structure of the group. If you go to the Langland's dual side, you will have your compact structure for the Langland's dual group given to you, and it's the same Riemann surface. So there is a natural conjecture to be made, and we've proven the things that you can prove mathematically rigorously. So the duality between the fibers, as I told you, was a collection of tori in each fiber. So if you look at the dual, a billion varieties, and those things match, but it's not really a concrete proof of the duality. The conjecture here with David Baraglia is that the dual brane to this one, the dual brane is an ABA brane fixed. And you can see who the involution is going to be. It's going to be some kind of dual involution where what we're taking is really the same type of thing. We're still taking our real structure on the Riemann surface, which will remain the same, but we're taking the compact dual evolution here. So this is the compact form, compact for GC. F star minus f star rho L phi. So you can do the test. You can do the test of dimensions, the dimension of the intersection with smooth fibers of this brane plus the dimension of the intersection of this brane with the smooth branes has to sum to total. Yes? L, yes, thank you. Thank you. Yes, it's important. It's the compact structure for the dual form. And you can ask the same about these branes that we saw yesterday. Yesterday we said if you look at the fixed points for this involution, you have G Higgs bundles, real Higgs bundles, giving you real representations of your fundamental group. What is the dual brane? In principle, we don't know much. There's not been proven anything, but what we can conjecture in this case, so conjecture with David Baraglia back in 2013, it was that the dual brane, the dual BBP brane is given by HC Higgs bundles, where I should tell you who HC is. HC is a complex subgroup of the Langlands dual group, where, so for HC was known as the Nadler group. So David Nadler, who's a mathematician in Berkeley, was studying Grassmannians, and he produced a way related to Langlands duality of constructing complex groups associated to real forms of a Langlands dual. And those are the groups we propose should be the case. There's the same type of support that we have for this conjecture, but there's nothing proven. Hopefully by next year, Lucas Branco is a partial proof. In some cases, he's a student at Oxford with Nigel Hitchin. So in 3 groups that I'll tell you about which ones they are, he has a possible proof. Hopefully in his thesis will be about that. So that's the question that many, it's the same that it would mean to prove Langlands duality concretely with Fourier-Mukai transform type of thing. But even the idea of how do we prove this physical statement, or a mathematical proof. Those, yes, there are properties that the dual brane has to satisfy, but those are, everything comes from physics. So those properties are usually easier to check. There are conditions on the dimensions that they have to satisfy. From string theory, I think they have some ways of checking, but I can't find them. It's strange. It should be, or people think that it should be, some kind of way that you have when you look at Fukaya categories and derived categories, right? You have a duality, take an object in one, is our Lagrangian. How do we go to the derived category? How do you obtain the dual object? So that's the procedure that should appear here, and it's the Fourier-Mukai transform on some space. That's why it's useful for those branes to be expressed in terms of spectral data, of line bundles on curves. But beyond that, I don't know what the methods of Lucas Branco, but he claims that he has a more mathematical proof of these things. For us, it's more about checking the physicists' main properties that they say these things have to have, and the numerology. There's a lot of numerology going on. Yes? It's constructed? So it's constructing using the maximal split form of the real form. So you have G, you have a maximal split form, and you'll look at the other side in Langlands duality, and through that you're going to construct it. It's in a paper called Grassmannians, Luke Grassmannians of David Nadler, and example. So an example is if you take any split real form, in the dual side is the whole thing. Okay? So any split real form in one side, in the group, in the Langlands dual group, it will be the whole complex group. How do you see this intuitively? How can I remember that? The ABA brane, I told you, the BAA brane, yesterday I told you for split real forms, we get a finite cover of the Riemann surface. So that's a discrete intersection, is dimension 0. And I just mentioned that the dimension of the 2 branes has to sum up to its full dimension. So it means in the dual side, it has to be the full dimension of the fiber. So it will end up being the full group, giving us that brane. So that's a way of remembering. Another way of remembering is that two branes will be complementary to some extent, in the same extent that Hitchin was taking in 2007 for the complex groups. So if here you have a brane given by spectral data which is invariant in an evolution, most likely in the dual side you'll have spectral data which is anti-invariant with respect to that evolution. And when you check those things with this brane conjectured, it does match. When you check the other things, then it does match. So, yeah. Any other questions? No? I have 20 minutes. Okay. So, just a little bit more. We're not going to talk about the ABA branes anymore, or the three manifolds. And I want to focus on both these real Higgs bundles. So let's keep the real Higgs bundles here. The real Higgs bundles and different cases that we can have. So we mentioned yesterday we could have the split real form giving us finite intersection with the smooth fibers. So the cases we looked at for these BAA, where if we had finite intersection or zero-dimensional intersection with fibers, and we said that this was the case, for instance, of G being a split real form. So an example of this is SL and R for SL and C. So why is this so interesting? One of the reasons, or interesting at all, one of the reasons is that once you have finite intersection, it means that you have finite points in each place. And in order to understand your brane, this is your ABA brane. So these give me, the BAA, the real Higgs bundles. And in order to understand it, one thing that you can do is you can take a loop in the base and see how it acts here. So this is a monodromy action for this cover. So you get a finite cover, and study monodromy. So the monodromy action will take loops in the Hitchin base, will look at the action on the Hitchin vibration on this integrable system, and the orbits of your monodromy will in fact be the connected components of your brane. So it's a way of understanding connected components of the brane. In the case of SL and R, we know it. I did it a few years ago. In the case of any rank 2 Higgs bundles, and with any twist, so Higgs bundles where the Higgs field phi, and we saw some examples already this week, the Higgs field phi goes from E, instead of from E to E tensor K, it goes to any line bundle, or any line bundle. This we did with David Baraglia last year, and I think for higher rank, very soon you'll have a paper by David, any rank, soon, by David, where he can extend the procedures that we had. So this allows you to see the monodromy action in terms of the fixed points. You can use it for calculating connected components. So here I could calculate the SLNR connected components. With this one, because even though it's rank 2, because it's twisted by any line bundle, we could calculate connectivity for the symplectic group with rank 4 or for the special orthogonal of rank 5. We could do things for higher rank just by playing with the trick of having any twisted line bundle. With this one, you can go to any rank. So this is what you can do when you have finite intersection, you have a cover. Now, another case that we saw, the case that we saw yesterday was positive intersection. And I don't want to say much more. This is the case that we studied more in depth, the spectral data for SUMM Higgs bundles, and we saw that we obtained Jacobians. But there's a case that we didn't pay much attention to, which was what happens when it lies inside the singular fibers. So the last case was when the BAA brane, so the BAA brane lies entirely inside inside the singular locus of the Hitchin vibration. Or over, lies over singular loci of the Hitchin base. And this will, in fact, happen in many, many cases. It relates to the question we had yesterday of how do we know which points in the Hitchin base give us the brane on top. So you look at your points in the Hitchin base, and many times will be all singular points. In these cases, you can try to understand the Hitchin vibration and the intersection with this brane through new methods, because the old methods were just for smooth fibers here. So let me tell you an example in a few minutes of when does this happen. So if you take G, the real form, for instance, the special linear group with coefficients, the octonions, the quaternions, or you take SO with quaternions, or you take the symplectic group with signature 2M to M, so the same signature. In all of these cases, what we could show with Hitchin was that it lied inside the singular fibers, and not only that it lied inside the singular fiber, but something very particular happened. So let's take a Higgs field here. Let's take a Higgs field here and see what happens. And I'll tell you the structure of the Higgs pair, and maybe you can figure out from there what's going to happen. So the Higgs bundle here is E symplectic. I should put probably a 2 here, so I want them to be even. So, or not, depending on the notation. So it's going to be a symplectic 4M vector bundle. And the Higgs field will be such that it's isomorphic to its symplectic transpose. So this is symplectic transpose. So it's not that hard, as a pair is a symplectic vector bundle and a compatible Higgs field, but the dimensions are very particular, and the fact that this is isomorphic to a symplectic transpose. So when you look at the Hitchin vibration, remember the thing that you had to do was understand how the characteristic polynomial of the Higgs field appeared. So let's do the characteristic polynomial for this thing. And in fact, the characteristic polynomial of these three groups will be very similar, and that's why we can put them together. So when we look at the characteristic polynomial of phi, what we find out is that it's actually a square of a polynomial, let's call it p lambda square, which is a Pfaffian associated to the Higgs field. And so we're going to have something like lambda to the 2m plus a1 lambda to the 2m minus 2 plus am. Here. And here a square. So this is how the characteristic polynomial will look. Is ai is the section of one of the powers of the canonical bundle to I. And the characteristic polynomial for the three groups, that's how it looks like. So it's, in particular, is reducible, so it's singular. So it lies inside the singular points of the Hitchin vibration, but you can still work with them. So you don't have to worry too much. You do something similar to what we were doing for SO2n plus 1. We declare now, this is our polynomial p lambda, so this is p lambda, and we're going to say that that is what gives us the spectral curve. So equal to 0 defines the spectral curve S. And you can see something else that's going on here. Something else is that it's only even degrees, because only the Pfaffian appears, but the eigenvalues appear in pairs. And so you have here the involution, some involution tau, sending lambda to minus lambda. So lots of ingredients that we already saw for other real forms or complex groups are appearing here. So when you look at the spectral data, you have your curve here. Now it's a 2m to 1 cover, not a 4m. And it has an involution tau. So you can construct a quotient that we did before by tau and get an m to 1 cover. And you can try to understand the spectral data from this perspective. And when you look at the same thing that we were doing before, we were looking at the co-kernel of our characteristic polynomial to get the spectral line bundle. Now, if we look at the co-kernel, here every eigenvalue appears with degree 2, so, or order 2. So our eigenspaces will have dimension 2. So our eigen is not going to be an eigenline bundle, it's going to be an eigenvector bundle. So here, what we're going to have is a vector bundle V, a rank 2 vector bundle. And because we need certain structure on the Higgs field and on the vector bundle, you might remember that when we're looking at symplectic vector bundles, we needed some invariance under an involution or anti-invariance, and that's the same that's going to appear here. We're going to ask our vector bundle to be preserved by the involution, so when we act by it by the involution, it's going to be preserved, and we're going to have fixed, so we're going to ask for semi-stability, because if it was unstable, when you push it down, you get something which will give you an unstable Higgs bundle. So semi-stability of this vector bundle will imply semi-stability of the Higgs field and vice versa. And the last thing you'll need is a condition on the vector, on the determinant, so that the determinant downstairs works fine. So fixed, some fixed determinant, which is some power of the canonical bundle. Once you have all these three conditions, you'll get your first Higgs bundle here, you'll get your SLNH. So this is non-abelian. This is what we call the non-abelianization of the vibration, because you don't have Jacobian varieties anymore. You have these spaces of stable vector bundles on your curve. Now, you may ask what happens with these other two cases, and what's going on is something complementary in these two cases. Because you have an involution acting on your vector bundle, you have an involution acting on, so those two groups are subgroups of SLNH. So your involution acts also on the determinant. So it's acting, the involution, tau, is also acting on the determinant of V. So this is the second exterior power of the vector bundle. And that action over each of the fixed points is plus or minus 1. This is a line bundle. We have a plus or minus 1 action. Depending on if it's 1, or if it's minus 1, it'll give us SO or SP grips. So the action, this action determines whether the pair is SO. So this group here, if you haven't seen it before, this is what people call SO star, the group SO star, and this is what people call SU star. So depending on this, you'll get the SO star or the SP, if it acts as plus 1 or minus 1. And that's how you figure out what the spectral data is for each of the groups. And then you can ask, okay, the definition is not that nice. It's rank 2 vector bundles which are semi-stable, preserved by an involution, and acted in a certain way by the involution on the determinant. It's quite complicated. It's not as neat as the Jacobian. But because you have theories of invariant vector bundles of any rank by any automorphism on a curve, you can use that theory to understand actually what these vector bundles with all these conditions mean really. And what you see is that actually what they mean is all these conditions are equivalent to saying certain parabolic, stable, rank 2 bundles on this quotient curve, on the intermediate cover. This space has been studied before. It's been shown in a paper that's not that short, that it's a connected space. So you know that your fibers, your intersection is indeed connected by looking at this quotient curve. I said certain parabolic bundles because the parabolic structure is actually determined by this action. You have your fixed points of the involution, your ramification points with certain action, and those fixed points, depending on a plus or minus 1, will give you weights here of 1/2 or -1/2. And using those weights and the one canonical subbundle, you have your filtration for your parabolic structure. So, yes? No. No. In non, so we should have said this. For these real groups, we don't have that, right? Because for split forms, we have a finite intersection. So that's dimension 0 on the base. So if we won't have integrable systems anymore. And that's why, while some people call the real Hitchin vibration, Hitchin and many others are more against that version because it's not really a Hitchin vibration. It's not an integrable system or a proper map. It doesn't have any of the properties that the original vibration had. It's better, or it could be better, maybe, to think about just intersection of these spaces with the vibrations. Yes. So in the last 4 minutes, let me tell you something else that is very interesting about this integrable system and the correspondences, because we talked about Langland's duality here, but I want to forget about Langland's duality for a moment. And I want to ask you, what other correspondences can there be with the Hitchin vibration? What other correspondences can there be with branes inside the Hitchin vibration? Because Langland's duality tells us correspondences between certain types of brane and certain other types of branes. So it told us if we had an BAA brane, we went to, if we had a BAA brane, we went to a BBB brane and so on. But now I want to ask, what other thing can I fiber over the same base? What else can I put here such that there is a correspondence between branes, which is not the one that Langland's duality gives me? So Langland's duality told me that if I have a BAA, I got a BBB. But now I want to put something that gives me here another BAA, fibered over the same Hitchin base. And what you could do, you can try to approach this question in many different ways, but the way that we try to approach it with Steve Bradlow, so what I'm telling you here is the work with Steve Bradlow from last year, and with Steve Bradlow and Ian McIntosh of this year, is that what we're trying to do is understand ways in which we can get these correspondences, and the ways that we're approaching are by taking different representations of the group. So you can take minuscule representations for the same group, or for different groups, and you can take also isogenies. So the first thing is look at isogenies. So look at low rank isogenies to get correspondences between Hitchin vibrations. What are the low rank isogenies? Well, the low rank, let's start with the lowest ranks. So rank 2 and rank 3, there are not many isogenies. In fact, there are just 2 isogenies. These are between real multiples of real groups. And what we have here is the rank 2 is SL2. Sorry, am I confusing? No. Rank 2 is SL2R. Or SL2C, let's say. SL2C cross SL2C and SO4C. And here we have SL4C and SO6C. If you have, what we did with Steve Bradlow last year is understand these correspondences between the groups in terms of Hitchin vibration. If you look at the Hitchin vibration for these groups, they do fiber over the same Hitchin base. And since you have a correspondence between the vibration, you can do the correspondence between each of the complex fibers. You can look at the split real forms. So we looked here at SL2R cross SL2R, and here SO22, and here SO33, and here SL4R. If you look at these split real forms, they'll give you BAA branes in both cases. So you have a correspondence between BAA branes. And now, this is not Langland's duality. So we want to understand what is the map that sends one brane to the other. And the trick is the following. So you start with this side, and you want to construct the other brane. In this case, you have 2 Higgs bundles of rank 2. And I have 1 minute left. So I'll tell you in 1 minute just essentially what we're trying to do, or what we did. We have 2 Higgs bundles. Each of them has a spectral curve. So you have a spectral curve S1 and a spectral curve S2 over your Riemann surface. And in order to construct your rank 4 cover, in this case, what you're doing, in case number 1, in the rank 2 case, what you do is you take the fiber product of these 2 curves. So you take the fiber product over the Riemann surface of these 2 curves, and in fact, this is not much more than what we need. This is going to be a 4-to-1 cover. And there are a few important points here. We saw yesterday that these curves were or we mentioned that for SO2 and C, the spectral curve, Hitchin spectral curve, is singular, because when you look at the Hitchin at the characteristic polynomial of your Higgs field, it's a rank 2n polynomial whose last coefficient, last a, is a Pfaffian, is a square. So it's not, it's singular over the zeros of your last coefficient. So you always have a singular curve, and you may wonder, how do I do spectral data? Hitchin, what he did was normalize this curve and define line bundles over the normalized curve. But another way of doing it is by starting in this side of the story. What you get here, so if you define this as a curve, this is a canonical desingularization of your curve that you wanted. So this gives the canonical desingularization of the SO4C spectral curve. What, sorry? Yeah. So you get the resolution already by doing this procedure. And you may ask, that worked out because we had two different Higgs bundles. We're putting some assumptions here. We're asking for the two Higgs fields to have different spectral curves. So if we had the same, something different would happen, and I can tell you what happens. So in the last 2 seconds, let me tell you how can we adapt that method to this one here. The way that you adapt it is say, okay, I have only just one Higgs bundle, but I can still do fiber product of the same curve with itself. That's still allowed. Now it's a rank 4 curve, so we'll have a rank 16 here. So this is not the curve that we want, because remember, we were looking for a 6 spectral curve. But that's okay, because actually, when you look at this curve here, you have a lot of things. You have an involution here that switches 2 factors, so you'll have to quotient by that involution. And when you look at the equation of this curve, you'll be something of the form a polynomial square times another polynomial. This will be of degree 4, and this will be of degree 6. This polynomial, when you symmetrize under the involution, will give you the canonical desingularization of your SO6. So this one is, after symmetrizing, the canonical desingularization of SO6. So you get the singularization. The spectral line bundles, there are, in the case of SL2 cross SL2, it's just a pullback, but in the other case, you have to take some invariant space. And you can go further and ask more questions. The things that we're doing with Steve and Ian McIntosh are now looking, instead of real forms inside real forms inside complex groups, we're trying to think about complex groups as real forms of other complex groups. So here, you could think of SL2C, instead of looking at SL2R cross SL2R as a BAA brane, I want to consider a BAA brane coming from SL2C, inserted diagonally. So I can think of SL2C as a real form of the product. That gives me a BAA brane, and I can ask what is the correspondence that goes in the other side. When you look at the other side, what you're going to get here is the real form SO13, and the correspondence in this side seems to be even, well, a bit more interesting than the ones that we were doing before. So thank you very much. Not a duality, just a correspondence, yes. There are properties that we've shown for this correspondence here. So this BAA brane gives you a 2 to a 2G cover of the BAA brane you have here. And it's not 1-to-1, it's a covering. And the way that you know which components are covered, because not all the components of these are covered, and it's only the ones with certain second Stiefel-Whitney class. So you can classify the things.